Hari Om. Here we are continuing with the equation of pressure of the gas. And we found that the RMS velocity, as stated, is found to be independent of variation of pressure of the given system. Then we must find out on what all factors does that RMS velocity depend. It's a very important thing. So let us consider the equation again, and we can write this to be equal to P into V equal to 1 by 3 into M into V RMS square. But we know that pressure into volume, here we have taken the gaseous system, therefore for the gas we can have PV equal to mu R into T, where mu is the number of moles and R gas constant and T is the absolute temperature of the gas. So if you compare that with this one, we can have the equation that mu into R into T is equal to 1 by 3 into M into the RMS square. Alright. So, what I am doing here is we want to find the equation for RMS velocity, and therefore VRMS square will be equal to 3 times mu into R into T divided by mass, and therefore VRMS is equal to square root of 3 times mu into R into T divided by mass of the gas in kilogram. So this I can write in this way, that root of 3RT divided by M divided by mu. Mass in kilogram by number of moles of the gas. So this can therefore be written as VRMS is equal to square root of 3RT divided by M, where the denominator M represents the molar mass of the gas. That means mass of 1 mole of the gas it is. So from this very particular equation we can get the idea that VRMS that depends on, see this, VRMS that depends on what are factors. VRMS is directly proportional to square root of absolute temperature, and again VRMS inversely proportional to square root of molar mass. So RMS velocity that is directly proportional to the square root of absolute temperature of the gas. Temperature is RMS velocity is. Then inversely proportional to square root of molar mass of the gas means as the gas changes, the molar mass changes, and therefore RMS velocity also changes. So RMS velocity is depending on the molar mass means the RMS velocity depends on the nature of the gas. Okay. So these two are the quantities on which the RMS velocity of the gas depends. Now let us continue with the fact again that we got the formula there already, that is VRMS is equal to, let me take that formula again, VRMS is equal to square root of 3 times gas constant in the absolute temperature by molar mass, and if I square this one we get VRMS square equal to 3RT divided by molar mass. Rearrange it. And as we go like this, and we can find that molar mass into Vrms square will be equal to 3RT. And if I multiply both sides with half, I get half into molar mass into Vrms square will be equal to 3 by 2R into T. So we are getting a very important relation here, that is kinetic energy of 1 mole of a gas. Kinetic energy of 1 mole of a gas is equal to 3 by 2 times RT. And we got the statement that kinetic energy of the gas molecules is directly proportional to the absolute temperature of the gas. You are getting the condition here. Okay? Now, this is for 1 mole of the gas, therefore, what is the kinetic energy of 1 molecule of the gas? It's always a question. Now, if I take 1 mole of the gas, it contains Avogadro number of molecules, and therefore, I can rewrite this as half into molar mass into Vrms square. This is mass, kinetic energy of 1 mole, then divided by Avogadro number. Na stands for Avogadro number. That will be equal to 3 by 2 times R by Na into T. Okay? Then this R by Na into T, I can take it as half M into Vrms square. That is this one. Okay? And this one together I can take it as 3 by 2 Kb into T. So this is actually the kinetic energy associated with the 1 molecule of the gas. That is equal to 3 by 2 times Kb. That Kb, which is equal to R by Na, is called Boltzmann constant. Okay? So here again, kinetic energy of 1 molecule also depends on what we call the absolute temperature of the gas. Okay? So we got the kinetic theory out of this one, and all these equations are very, very important. And one more point to discuss here is that again we start with what we call pressure of the gas, and from that pressure of the gas, let us see, we have come up to what? Here. Now let us see this equation. P equal to 1 by 3 m by v into Vrms square. Okay, the same thing I am repeating. Now here I do one rearrangement in another way that suppose I take P equal to 2 by 3 into 1 by 2, 1 by 3 remains. Then m into Vrms square divided by volume. An arrangement like this is possible. Then this half m Vrms square, that is m is the mass of the gas, and therefore you can have that as what you call the kinetic energy of the gas. kinetic energy associated with m mass of the gas. Okay. So kinetic energy divided by volume of the gas. So we can define this to be kinetic energy per volume, that is energy density of the gas. Therefore, pressure P equal to 2 by 3 times E. An equation like this is also possible, where E is equal to this one, that is equal to energy density of the gas. Energy density of the gas, we can say. So, kinetic energy equation. Molar kinetic energy depends on 3 by 2 RT, and molecular kinetic energy depends on 3 by 2 kB into T. Then, energy density and pressure, how they are related. So, all these small equations are very important for entrance also. So, all these equations are obtained from what you call the pressure of the gas. That equation you must by heart, this one, and all other equations are obtained from this particular equation.